Any doubts related to previous classes? If you have, please quickly ask. You have time to ask. At last, I won't be able to answer because I don't know how much time I'll take for this topic. So if you have doubts, you quickly ask here in starting so that there will be some flow in the concepts. So let me know if any doubts you have. Otherwise, I'll move on and quickly I'll finish this. So I think everything is clear to you. Whatever I taught in the previous classes, it is perfectly clear. So now I'll come to the another topic. I have so many topics, but one of them it is this one. So here we can see I have given heading that is diode connected transistor. So do you have any idea related to this? What is this diode connected transistor? Sometimes in the exam they don't mention like this diode connected transistors. They sometimes they give only the diagram. What is the diagram? How it looks like? So that we'll see here. So diode connected transistors, as I have written in the theory, that if collector is shorted to base, it behaves as a diode. Such transistor is called diode connected transistor. Arrowhead indicates the direction of electron current in emitter. That I'll show you in the diagram first. You just see the diagram here. It is, I have one transistor. This transistor, it is looking like this. This is base. This is collector. And this is emitter. So these three things are there. And this voltage plus and minus, I'll say this is VBE. And this, I can say this is plus and this is minus. With respect to this only I'll take. And I'll see here current is flowing in this direction like that. Okay. So this transistor is nothing but PNP transistor, sorry, NPN transistor. NPN transistor. So this transistor can be converted in this format, like this is the actual diagram for this. Here, this base is this one and this is emitter, because base and collector both are combined here in this. Its internal structure also I'll show you how it looks like, how current flows. That also I'll show you. But here we can see the arrowhead indicates the direction of electron current in emitter. This is arrowhead. This arrowhead here and this arrowhead, this we can say. So this arrowhead, it shows the direction of electron current in emitter, means electrons are moving from this terminal to here, but current is flowing opposite to that. Current through this transistor will be controlled by the voltage VBE applied across emitter junction. Across this junction, whatever voltage we apply, that will control the current through this. So this is nothing but the emitter junction here we have. So the current flow is shown in this diagram here. You can see. That is, I think, clear. Now, that this diagram now can be converted in the other format. What is that format? That will be like this. We have three regions. This is N, P and N transistor. This one is collector junction, this one is emitter junction, and this one is base. And this base is directly connected to this collector. And this is my base and this is my emitter. So I'll say this is plus, this is minus, and this voltage is VBE. I'll say like this. Here I have electron in majority. So, and electron, this is emitter terminal. So emitter is always supplying an electrons to the other regions. So electron which is here, any electron which is here, it will move towards collector. So this is the electron movement direction. And this junction, it is collector junction, and this junction is the emitter junction. These two junctions we have. So we can see the current direction, it will be definitely this direction. Current direction will be downward. Electron movement is upward. So this circuit can be converted in this format. So we have the format like this. So that is the flow of the current shown in the figure. So we can understand from this. Here we applied positive voltage, means this terminal, means the emitter junction, it is nothing but a positive forward biased. That is this forward voltage. So electron will be injected from emitter into base, in this case here like this. These electrons then cross the collector junction due to built-in potential. See here, these electrons, these are crossing this junction only because of built-in potential across this junction, because there is no other potential exist between collector to base. If there is no potential exist, external potential exist here, so it has only its internal potential, that is built-in potential. That built-in potential only will help these electrons to move into the collector region or to cross this junction, collector junction. So we can say the flow takes place through collector junction, even though the collector and base terminals are short together. See, we can see these are shorted together, but the flow it is coming only because of this built-in potential. That is why we have the transistor effect in this, but it is working as a diode here. So now what is this current value I naught? That I value, what is this value? How we can calculate this value I in a transistor, like diode connected transistor is given to us. So they wanted to know what is the current I. So that current, it can be directly written as, I can show you in the next slide. Here we can see, I, that is the current, will be equal to I naught e to the power V divided by eta Vt. That is approximate current, because -1 also comes, but that we will not consider. As compared to 1, we have this value in large. So this can be written as like this. But here, what is this I naught? I naught is nothing but the I E naught, means the reverse saturation current in emitter junction. Reverse saturation current in emitter junction means JE, across JE. And eta we will consider it is 1 for germanium, if we have germanium material. Otherwise it will be given to you in the exam. or V, that is this voltage, that will be equal to VBE, emitter junction voltage, forward voltage, that be VBE we have. So this expression now can be converted into this format, IE naught into e to the power VBE divided by VT. I can write this. This is my actual expression. So sometimes in the exam, they will be asking questions like this diagram will be given to you, whatever I made in the previous slide, and they will be asking the current through the diode, the transistor. So we should have clear idea in that case. So like this, I have written expression here, that is IE is equal to IE naught, I is equal to IE naught e to the power VBE divided by VT. I means this is IC, collector current, remember, collector current, that is shown in the diagram, that in the first slide only have shown that. So we should remember this. So what is the current, or what is the current expression in this case? So here the question, which is based on this previous theory, that is in the figure shown. What is the figure? Figure is same like earlier, whatever I made. It will be like this only. This is base, this is collector, this is emitter. This will be my figure. This plus and this is minus sign. So I will be having this BVE. Okay. So here what is happening? This is the actual diagram. Here current they wanted to know. What is the current? So the current I they wanted to know. In the figure shown, BVE they have given, and reverse saturation current this much at room temperature. If they are talking about room temperature, VT value will be how much? That will be 26 millivolt. Directly we will be right. Okay. And IE note how much they have given, that is 10 to the power minus 13 amps. So all the values I have, I can keep. VBE they have given 0.7 volt. So I'll get I is equal to 10 to the power minus 13. Direct formula I'll apply here. V e to the power 0.7 divided by 0.026. This is point. So this, from this if I calculate, I'll get answer. What is that? 49.26 milliamps. This is the current which I'll get from this. So it is a straightforward question. There nothing much is there in this, but we should know the things. We should know all the formulas. We should know the concept behind any question or any theory. So that is the main aim here. So I think it is clear to everyone. So anything if you want to ask, you immediately ask. Otherwise, I have another thing to start. I have questions, but I'll not take questions in today's class. Very less few questions I'll take, one or two, because I have a lot of theory to complete in this class. So here we'll see. I think whatever I taught, it is clear to everyone. Anything which is not clear to anyone, please quickly ask. Otherwise, I'll move on. So here we can see the early effect. Early effect, as I written here, it is proposed by James Early. That is why its name was reflected in the theory. So based on his name, that theory came. So that what is this early effect? So that early effect we'll see here. First of all, you just make one diagram. That diagram, it will be like our BJT. This is P region, this is N region, and this is P region. P and P transistor I will take, and here I'll write this is my emitter, and this is my base, this is my collector. So I'll write this. So here I have emitter junction, I have collector junction, okay, and I have base, okay. So what is happening here? I'll do one thing, I'll apply some voltage across collector and base, and that is VCB. And this is depletion region, and here we can see this because collector is heavily doped, so very less region it will cover in this, but if it is lightly doped, so it has more region in this, we can see. Okay, so this is the diagram. I'm not talking about emitter, terminal and all these connections. I will just talk about this collector junction, and this is base emitter junction. So what is happening across collector junction? See, in active region, we know we use transistor for amplification in active region only. So my aim will be mostly make my transistor in active region only, because it is mostly used in active region. So when transistor is in active region, JC, it is operated in reverse biased, and JE it will be in forward biased. So JC it is in reverse biased. How? Because of external voltage, that is VCB applied here. This is reverse biased voltage. So now suppose I'll increase this reverse bias voltage, the depletion region width of JC junction increases. And because base it is lightly doped, so it will be more penetrated into the base region, and collector is moderately doped, so it will be less in the collector region. When I increase this voltage, this is more and more uh, deeped into the base region, means base region is covered more by this depletion width. So that is I have written here, since base region is lightly doped in comparison to the collector, depletion region will penetrate more into the base, due to which effective base width decreases. Effective base width is what? This is my effective base width. Means this is my effective base width. Actual base width was how much? That was up to here. I can show you. This was my actual base width. But effective base width is this much only, up to here. Because this is covered by depletion region. This is covered by depletion region. This much. This much is covered by depletion region. So this effective base width, it is now decreases. When I increase this voltage more and more, this effective base width continuously decreasing. And now this decrease in effective base width due to increase in reverse voltage is known as early effect or base width modulation. It is. This concept is known as base width modulation. Means we are modulating base width. Whatever actual base width was there, that is not present as of now when we increase this reverse bias voltage. So with this reverse bias voltage, we can control the recombinations in the base region, because we are reducing the effective base width. So recombinations we can reduce. So that recombination current, that is base current, that can be reduced. If it is reduced, then the flow of this majority charge carriers will be faster. So more current will be flowing through the junction. So like that, many changes will be coming, but this is the major concept here, main concept, that how base width is affected. Now, this base width effect is known as early effect or base width modulation. Now, it has some consequences. What are those consequences? When this happens, when this effect changes, this base width changes, this early effect comes, then some consequences are there. What are those consequences? Those are three consequences. One is alpha. Alpha increases. How alpha increases? See, we'll see how alpha increases. Suppose what I am doing VCB increase. I have increased VCB. This voltage I increased. So effective base width, what it will do? It will do effective base width. I can say WB, base width. It is not the depletion region width, it is base width. This base width, it will get reduced. That is effective base width. I can write E here. That is effective base width. It reduces. So when this reduces, what will happen? Number of electron hole recombinations inside base region, that will be reduced. Electron and hole recombination reduces because effective base width reduces. This recombination reduces, then what will happen? Our beta, that is called beta star, I'll say now, that beta star, it will get increased. If it will increase, it will get increased, what will happen? My alpha, that is this, will get decreased. Sorry, alpha will not get decreased, alpha will get increased also because of this. We can see in other ways also. What are other ways? Other ways are alpha equal to, that is the current, that is IC divided by IE. So when this recombination reduces, IB reduces. IB reduces, it means IC will get increase, but very lightly, very small increment is there in IC. So when IC increases and IE, it is same, it is not changed. So alpha also increased here. That is the thing. Because recombination reduces, IB reduces, because IB reduces, then IC obviously it will get increased because the large number of carriers will be reaching to the collector junction. So current will get increased. So that is why alpha increases. And in the same way, beta also. Beta is equal to how much? This is equal to IC divided by IB. Now here we can see IC increased, at the same time IB decreased. So numerator increased and denominator decreased at the same time. Then beta, it will get increased in the large extent. Here alpha was increasing in very small extent. So beta will get increased in the large extent. So how it is? Suppose I'll say alpha, it was 0.99 and it increased to 0.992. This much increment it is there in alpha. That is alpha. Now what will happen to beta? Beta will be here Wow, how much it was? It was 99. Now how much it will be? It will be here 124. You just calculate by taking alpha this, you calculate beta, you will get this. It is how much? 124. You can see there is a minute change, minute increment in alpha, but we have a large increment in beta. That change we can see here. So that is the thing happening inside. So there is a small change in alpha, there is a small change in VCB, and alpha we got large change in beta. So we got amplification, more amplification in the output. So that is the thing happening here. Now I think it is clear that alpha increases. How it increases, that we understood here. Second thing, ammeter current increases. How ammeter current increases? We can see here IE, that is equal to IPE. I can say in PNP transistor. This is whole diffusion current also through JE, through this emitter junction. So IPE, that will be directly proportional to dP divided by dx. That is for sure, that IPE is directly proportional to dP by dx. This is concentration gradient or majority carriers gradient in emitter region. So that is this current. So suppose what will I do? I am increasing VCB. VCB I increased first. So effective base width, that is WB effective, it got decreased. Because of this, effective base width decreases. Effective base width decreases means delta X, that effective base width, that is, I can say it is decreased. That recombination places, those decreased. That recombination space, it is decreased. So because of that, if it is decreased, what I will get? I'll say delta P divided by, or dP divided by dx, or delta P divided by delta X, it will automatically get increased because delta X decreases. This whole concentration, it will be there, that is constant, but delta X, it is affected. Because of this delta X, this delta P by delta X increased, and if it is increased, then from this I can say IPE also increased. If IPE increased, it means IE also increased. IE also increased. So we can see there is a small increment in emitter current, very minute increment, but IC is having more increment as compared to IE, because recombinations are reduced. First thing, IE increased. Second thing, recombinations reduced. So that both effect is added, and that is coming in IC. So IC is increased in large extent as compared to both IB and IE. So here we can see emitter current, that is also increased with this reverse bias voltage. So I'll say something. The current passing through emitter junction depends also upon the voltage VCB applied across the collector junction. So the emitter and collector junction are called interactive junction. These are not independent junctions. Emitter junction and collector junctions both are not independent. These are interactive junctions. If we change something in one junction, there will be an effect on the other junction, current and all. So there is a interaction between emitter and collector junctions. So these are not independent, remember this thing. So that we can see here that emitter current also increases, but it is not increased in that amount as IC increased. IC is the overall increment that was added by IE and IB. IB decreased and IE increased. So overall IC is increased in large extent. So these are the things. These are 2 points here we need to remember that first alpha increases, second emitter current increases, and emitter current increases says it also says that there is a interaction between emitter and collector junctions. So those are the things here. Okay, whatever something you asked, I think I have not seen. If base width decreases, how does it affect the P region width? P region width means which P region? It is collector region or it is emitter region? Which P region you are talking about? Emitter region. So see, emitter region, it is not affected. Emitter region, it is because that emitter junction, it is that emitter width, it is constant. It is not changed. Emitter width, it is not changed. So emitter region, it will not get changed. So whatever charge carriers are there in the emitter region, those will be constant. How does delta X decreases? Delta X, see, what is delta X? You understood or not? This delta X is the change in X in the base region. This is base region delta X. So earlier base region, it was having more delta X. It was having more delta X. You can see base region, this is delta X. I have not written here, but it is delta X. This is delta X only, this one, up to here only. So this delta X, it is reduced. Earlier, delta X was how much? This was the delta X earlier. So earlier, this was the delta X. That is why you were having delta P divided by delta X this much. But now, delta P is same because same number of charge carriers are entering into the base region. So delta P, it will be same. Delta P is not changed. But delta X is reduced. Delta X is reduced. We can understand thing that in the small region, delta P by delta X will get increase. I think you understood this. Okay, yeah, that's good. So that is only because charge carriers which were entering into this region, those are delta P. So those are same. Those are not changed. Same number of charge carriers are entering into this region. So delta P, it is constant. It is constant. These are not changed. But delta X, it is reduced. That is why this delta P by delta X reduced. That is why this gradient increases. So this will increase IPE. So these things we can understand clearly. Okay. Any doubts if you have, you can ask now, later also. So this is, I think, clear up to here. Now we'll come to the another point. Emitter current increases. So that I discussed already. This I have taken once again here, but that is not required here. So emitter and collector junctions are interactive junctions, that you remember here. Those two are interactive junctions. So now we'll move to another point. That is third point here. The punch through or reach through that can occur. Punch through or reach through can occur. That we'll understand. What is this punch through and reach through? So here I have written something. What is that? If VCB is sufficiently large, because VCB we are increasing continuously and we are seeing the effect of VCB. So if it is sufficiently large, the depletion region can penetrate fully into the base region, because base region already it was very small, and we increased VCB, so that base region, that effective base region, it is getting reduced again and again, and depletion region, it will be penetrating more and more into the base region. So effective base width becomes zero at some point, at some voltage, at some VCB. So at this value of BCB, when our effective base width becomes zero, that voltage, that is, we can say, uh, breakdown voltage. But here we are not talking about BCB, we are talking about this uh, effective base width. What is happening with this? So this is called punch through or reach through, means there is no effective base width now, means there is no recombination current now, means there is no base current now. So nothing is happening, means all the charge carriers which are coming from collector emitter are getting into the collector region. There is no base current at all. So because of that, there is a effect that this base width, it is getting reduced to zero. So this is called punch through or reach through. When punch through occurs, what will happen when this occurs? The concentration gradient becomes infinite. That is, I told just now that concentration gradient is delta P by delta X. Now what is happened? Delta X is, delta P is same, but delta X becomes zero. If it is zero, then it will become infinite. Means IPE that was directly proportional to this, now it is proportional to infinite. So it becomes infinite, and also the current gets electrically shorted. So collector gets electrically shorted to the emitter. It is not physically shorted, but it is electrically shorted. Due to this, a heavy current, due to this, 1 minute, a heavy current can flow through the transistor, which can permanently damage to the transistor. It can permanent damage to the transistor. Therefore, punch through should be avoided always. There should not be any punch through in transistor. So that can be possible. So that possibility is there if we increase continuously VCB voltage. So this effect is called punch through effect. So here we can see what is happening because of this punch through. Our transistor, it can permanent damaged. Okay, so we have some points related to this. What is one point is a BJT gets damage if either punch through or breakdown or thermal runaway takes place. Punch through, breakdown or thermal runaway, all are the things in which our transistor will get damaged. So there is no theory that it will be safe. If it is safe, it is your luck, otherwise it is gone. So we should avoid this punch through concept here. It should not be reached. So that is here one point. So we need to remember this punch through, thermal runaway, and breakdown reason. All these things we should remember. Now, second point, a BJT has two breakdowns voltages. A BJT has two breakdown voltages. One is breakdown voltage VCBO, the breakdown voltage of collector junction when emitter is open circuited. That I think I have shown you, I have given you that breakdown voltage of collector junction when emitter junction is open circuited. Second breakdown is the breakdown voltage of emitter junction when base is open circuited, VCE. So we can say in this there is no emitter, means emitter is open circuited. In this there is no base, means base is open circuited. So these are two breakdown voltages we have. So the breakdown voltage of the transistor when base is open circuited, that is VCEO. Now what is the relation between these all these values? If VCE is greater than or equal to V breakdown voltage VCEO, the breakdown can happen in transistor. It can be possible when it is crossing this value. So that this value VCEO is equal to BVCBO square root 1 by beta is n root of 1 by beta. So where n is a constant, where n is the constant, it is a constant value. So this expression we can remember. Two breakdown voltages we have, one breakdown voltage depends on other in this relation. So likewise we can remember this. So I have one question based on this. A transistor has beta that is 100 and breakdown voltage VCPO that is equal to 40 volt and N they have given 5. Calculate CEO. Can you answer me this question? How much I'll get in this? Quickly you answer. Quickly you answer this. I'm waiting for your answer here. You have all values with you. You just calculate and give answers. Okay. $15.92. Yes, you are right. Correct. I think you understood formula and everything. VPCEO that is equal to 15.92 volt. That is correct one. So I think you understood. You just remember this. Sometimes questions can be asked on this. So this was all about this breakdown voltages and this early effect. So how early effect give changes, so that we can see here now. This is my next one, VJT configuration. So here we can see VJT configurations. We have three configurations. One is common base, common emitter, and common collector. Configurations refers to how the three terminals of BJT are used. We have three terminals. How these three terminals we can use, that is referred by configuration. So how BJT is used in different configurations, based on that we named them, that is common base, common emitter, and common collector. As name given, common base means base will be common and other will be one of them will be emitter, sorry, input, and other will be output. So one terminal will be common, one is input and one is output. Like that we can use any device, any BJT, that is three terminal device. So that is configuration. So we have some things, three terminal device that will be used as common reference node. One will be the common reference node. Based on that only we configure them. So we have these three reasons. Okay. So how it is giving three reasons? See, our BJT that is of three terminals. We can see here. And this. Okay, this BJT is having three terminals. One will be input terminal, other will be output terminal, and other will be common terminal. That is common node, we can say. That will be common node. So this is plus and this is minus. This is plus and this is minus. Just I'll take 1 minute for you. Okay, now we'll start. So now we can see the diagram here. That is one is this first terminal, second terminal. We can say this is input terminal or this is output terminal. And this is common terminal. It will be like this, or we can say it is common node. So here we can see input terminal, we have current I1 and voltage V1. And at output terminal, we have current I2 and voltage V2. I think all these things you have seen in your network theories. So in network theory, two-port networks we have seen. So in that we have seen all this I1, I2, V1, V2, and this common node and all. So BJT is used like that only. So here we can see I1 and I2 are input and output currents. V1 and V2 are input and output voltages, and other is common node. So in this way, we will have some characteristics. BJT, those are BJT characteristics. So in BJT characteristics, we have some input and outputs. Some inputs are depending on some other inputs and outputs. So like that we will see. So these are current voltages plot which represent interdependence of four parameters. BJT characteristics means we have current and voltage plots which represents interdependence of four parameters I1, I2, V1, V2. So these are interdependent. So one is independent, other will be dependent on independent. So like that it will be. So here we can see we'll see the diagram and we'll see its configurations. We'll be having some configurations like we will say input characteristic. In input characteristic, a plot of input current I1 and input voltage V1 obtained by maintaining the output voltage V2 constant. Means what is, we'll see in the next slide, what is that? Here, that is input characteristic. In input characteristic, we have V2 that is constant. See, V2 is constant and V1 that is the function of I1. That is the function of I1. It means the input current I1 and input voltage V1 obtained by maintaining output voltage V2 constant, that is the input characteristic. So I think it is clear that in our BJT we always see V1 that is dependent, or that is the one function that is dependent on I1 and V2, and I2 that will be function 2 and it will be depending on I1 and V2. I think H parameters you have seen, it is based on those H parameters only. So I1 and V2, these will be independent parameters, I1 and V2. I'll say I1 and V2. These are independent parameters. And V1 and I2 are dependent parameters. So we have these 4 parameters, 2 are independent and 2 are dependent. These dependent are depending on independent parameters. So how they are dependent, that will be coming in your characteristics, like input characteristic and output characteristic. So this was input characteristic, and now output characteristic. In output characteristic, I1 will be constant. In output characteristic, I1 it will be constant, okay, and I2 it will be a function of V2 here. I2 will be a function of V2 and I1 is a constant. Here in first, V2 was a constant and V1 was a function of I1. So this was input characteristic and this was output characteristic. So like that it is happening here. We can understand, see all these things we'll see by one. All these input characteristic and output characteristic, this will be coming in BJT configurations. BJT configurations, we have 3 BJT configurations. In all these 3 BJT configurations, we'll be having input characteristic and output characteristics. So first we'll start with the common base characteristic. So here, like we have this common base characteristic. In common base characteristic, what is happening? We have our transistor like this. So we have emitter, we have base, we have collector, we have these 2 terminals. So this will be, I'll say like this. So I'll say it is VCB because this is collector and this is base. So this is plus and minus. Likewise, I'll say here plus and minus, and it is emitter and this is base. So I'll say VEB. Okay. This is VEB plus or minus. And here I'll be having current at emitter. I'll be having emitter current IE, and at the collector I'll be having current IC. See, current directions I always give into the device only. So based on sign only we'll decide whether it is coming in or out, but in starting we'll say all the currents are entering into the device. That is my aim here. So IB, IE and IC, all these three currents, these are entering into the device. So based on of their signs, we can say it is coming out or it is coming in. So like that only we can say. So this is common base configuration. We have base in common and other terminals are like this. So in this we have input characteristic and in this output characteristic. In input characteristic we have seen what our current, sorry, our voltage was constant, V2 was constant and V1 was depending on I1. And in output characteristic, I1 current, input current was constant and I2 volt current was depending on the output voltage. So like this, we'll see here. So this diagram you can see, based on this diagram, we'll have its two type of characteristics. One is input and other is output. So we can see input characteristic here. In input characteristic, it is a plot of IE and VEB. Whatever I told you, while maintaining VCB constant. VCB constant means output voltage constant, V2 constant. That is, I have already told you, in input characteristic, output voltage will be constant and input current will be depending on input voltage, like this. Sorry, this EB, IE is depending on VEB. So this is the diagram. So input characteristic, it will be like a diode characteristic. That one diode, it is a forward bias diode, and that diode, it will be acting like this. That voltage VEB is the voltage across the diode, and the current through this that diode, that is I. So we can see here, I have shown you three diagrams. So in three, V1 is this one, this is 2, this is 3. How it is happening? This VCV1, this is the voltage which is across the this collector junction. So this is VCB. This is the voltage across the collector junction, and if it is increased, this is C. We can see this is smallest value. If we increase, this graph will be moving upward towards this. So that we'll see how it is. So here, for a small value of EB, we can see here a small value of VEB, this voltage. The current IE is negligible. There is no current in the circuit. This VEB, we applied very small value at the input. So we have very small current. There is no current. Means our diode, our transistor, it is not in conduction mode. It is forward biased, but it is not in conduction mode. So it is negligible. But when we increase this VEB and it crosses a cut-in voltage, that is, some voltage will be there, that minimum voltage required. That it was like diode. It was like for diode cut-in voltage, that minimum voltage required to switch on the diode. So that is, so IE increases. Here I'll say VEB, sorry, it is not CE, it is VEB, that is equal to minus 0.6 volt for which transistor? For silicon. And it is minus 0.1 volt for germanium. And these are for NPN transistor, NPN BJTs. So we have NPN BJT, NPN type of transistor. For that transistor, we have these voltages, these negative voltages. So if we say this same value for P and P, so we will say VEB will be equal to 0.6 volt for silicon and 0.1 volt for germanium, and it will be for PNP. So it will be for PNP transistor. So we can see IE depends upon VCB. That also I told you long back that IE, this emitter current, it was also depending on the reverse bias voltage due to early effect. Because of that early effect, it was depending. So for a given value of VEB, this VEB value, for this EB value, for this EB, suppose any value, for this given value, the emitter current increases with increase in VCB. How? That early effect coming into the picture in here. So when we increase this, it was less, so emitter current will be less for the given value of BEB. Suppose it is I'll say how much, I'll say it is 0.9 volt. So if it is 0.9 volt, I'll make one straight line here. So for this given value, if CB it is lesser, so lesser IE will be there. If I'll increase VCB, higher IE will be there, and then higher IE will be there. I'll be having 3 IEs. So higher value of VCB, higher value of current will come. So that is the main concept. Here, what effect coming into the picture? Early effect, we can say. This current, and this current. So these are the 3 currents for the given value, for the constant value of VEB. I have 3 currents because of early effect. I changed this reverse bias voltages. So these reverse bias voltages only changing this IE current. That is why this graph, it is moving closer to the 0 axis here. So our cut-in voltage also reduces for this. We can say cut-in voltage reduces for early effect. So for a given value of VEB, VCB vary inversely with each other. So I think this effect you understood. So how current it is changing, that effect it is given here. And in the reverse way also we can see. I think it is clear to everyone. Any doubts if you have, you just ask, otherwise it is done. Okay, so now I'll move to another concept, that is output characteristic. This was input characteristic in this. What is the time? Time is 6:20. So after completing few things, I'll take a break. So what is this BJT characteristic here? In BJT, here I have written that IE depends also upon VCB due to the early effect. For a given value of VEB, emitter current increases with increase in VCB. Therefore, when VCB increases, input characteristic curve moves or shifts towards left. That I have shown here. This curve, it was moving towards left when this value, this early effect comes. Okay, so this was all about output input characteristic, and the input characteristic, it will be nothing but a forward bias diode, current and voltage characteristic it is. So now we'll come to the second thing, is output characteristic. So in output characteristic, what is the plot? Plot will be, it is a plot of IC and VCB, reverse bias voltage, while maintaining IE constant. That input current, it is constant, that I will maintain constant. Output current will be depending on the output voltage. So that is here. Output current will be depending on output voltage, that is here. So IC represents current passing through JC, and VCB is the voltage across the collector junction. The current through JC is superposition of the two currents. So what are these two currents? That I have written in the next slide. Here space was not there, so that is I have written here. One is the current due to carriers of emitter crossing JC, carriers which were coming from emitter and crossing collector junction. Due to that we got that IC current. And second is current due to the voltage VCB applied across the collector. So this current will be the reverse saturation current I naught, and this current it will be IPC that I already discussed. So IPC and I naught, these two currents are there. So because of these two currents, we have IC. That is I have written here. It is the superposition of two currents. That is IPC and I naught. So that is all about this. Now we'll see the curve. When IE it is 0, when there is no input current, when there is no input current, we are applying reverse saturation voltage, reverse bias voltage VCB. So we'll see the effect. Here we have this graph. It is like here we can see it will be like this. It is 0 point. So here IC versus VCB plot I have shown, and it will be identical to the diode characteristic. Forward biased characteristic are in third quadrant. Reverse biased characteristic in that is different thing. Whatever here it is written. So when IE maintained constant at a non-zero value, an additional current gets superimposed on the current as the output characteristic shift upward. See what is happening here. When this current there is no current applied. So whatever voltage you apply, there will be a zero current IC. IC will be zero. There is no IC. So you will have zero value of IC. So your transistor will be in this region, down region, and your transistor will be in cutoff region. That is cutoff region I have shown here. So now when we increase this IE when I'll increase, what will happen? Charge carriers will be reaching to the collector. When charge carriers will be reaching to the collector, and I will have some reverse saturation current also. So the combination of these two currents, I'll get some current that will be here. So first it will be increasing slowly, and then it is getting saturated at some value. And because maximum number of charge carriers are reaching to the collector, we don't have more charge carriers. So maximum charge carriers will be reaching to this, and I will be having this constant current IE1. Suppose I will increase some more current IE. Whenever I will increase IE, I will get IC increased, because IC is directly proportional to IE. So our output characteristic, it will shift in upward direction. Why it is in shifting upward direction? Because IE is increasing. Because of IE, I have more IC. IC is directly related to the IE. So in cutoff region, what is happening? Cutoff region, we can write something in cutoff region. In cutoff region, what is this? IE will be 0. In that case, JE, emitter junction, in reverse biased. And second thing, VCB, it is greater than 0. VCB, it is greater than 0. So this collector junction, it is also in reverse biased. If it is forward biased, RB, if it is emitter junction is forward biased, I will have some current. But if it is reverse biased, I will not have any current. So IE is 0. And this is BCB, it is already reverse biased. It is greater voltage, greater than 0. Greater than 0 means reverse voltage is greater than 0. So JCE, it is in reverse bias. Both are in reverse biased region. So here I can see IE, if I is 0, so IC will be only I naught. And if it is I naught, so for it is in nanoampere for silicon, and it is in microampere for germanium. These two things I'll have. And it is very small, or we can say negligible. So it means there is no current. So IC, it is almost 0, and our diode will be, our transistor will be in cutoff region. So this is the cutoff region concept. Now next will be saturation region. In saturation region, what is happening? I'll have a IE that is greater than 0. If IE greater than 0, my emitter junction, it will be in forward biased format. If it is in forward biased, and second thing, VCB, it will be less than 0. Here we can see VCB, it is less than 0. This part, it is less than 0. So if this part, if it is, then our collector junction will be in forward biased. Because if it was positive voltage, my collector junction was reverse biased, and now it is negative voltage, so my collector junction will be forward biased. If it is forward biased, both junctions are forward biased, so this indicates saturation mode. So in saturation, IC will vary with VCB and IE. VCB and IE. So IC will be changing here. It is varying like this. It is not constant. It is varying. It is depending on what? IE and VCB. On both values, it will be depending IC. So that is IE is the input current and VCB is the output voltage. Input current and output voltage. So that is, I have shown that in H parameter, what will have? I2 will be the function of I1 and V2. That is only. So this I have shown here in H parameters. That will see H parameters also we can see, but those are not required here. Those are in analog subject. So here only the required things only I want to show you. Third reason is we have active reason. In active region, what is happening? In active region, IE that will be greater than 0, definitely. So my JE will be in forward biased. Second thing, VCB, it is greater than 0. It is greater than 0. So my JC in reverse biased. So this mode, it is called active mode. This combination is called active mode. So see, whatever concept I'm taking here for common base, it will be same for common emitter and common collector. So now we can see VCB is a reverse voltage. Current through collector junction due to VCB is negligible. This VCB, it is reverse voltage. So current due to this, it will be negligible. That will be I naught. Negligible current. The current passing through the collector junction will be due to the carrier of emitters reaching the collector junction. That is second thing. this is negligible. I can say this is negligible. And second thing, IPE. IPE carriers will be reaching to the collectors, so they are providing IPC. IPC carrier, IPC current they are providing, and that will be equal to IC here. So this current it is negligible, and this current it is far greater. So now IC will be sum of IPC plus I naught. I naught is negligible, so I'll simply write it is equal to IPC. So that is the main thing we should understand. So here, what is this IPC? This is equal to alpha IE. That is IC. It is negligible. I can remove this. And because IE, it is entering into the device, so IC has to come out. So that is why I'll take negative sign here. Because one is entering and one is coming out. In my general consideration, I have taken all currents entering into the device are positive. So IE was here, IE is entering into the device, that is positive. So IC, which is coming out from the device, that is taken as negative value. So IC does not vary with VCB, but IC actively vary with IE. We can understand. See, there is a negligible effect of I naught. There is a negligible effect of VCB on IC, but it is not that much. Very negligible effect is there because of VCB, reverse bias voltage. Reverse bias voltage is providing this VCB, it is providing this current, and this current is negligible. So that is, I dropped, I kept it 0, and I have taken only remaining current. Remaining current is what? The current due to carriers coming from emitter junction. So that is I have taken into consideration here. So we can say now the transistor can be used as an amplifier if it is operated in the active region, because we have some current, we have some output current. In other two cases, we have seen the cutoff case, there was no current. In the saturation, there was a variation in the current. So there was not a constant value. We were not getting any constant value. So if it is operated in the active region, because in active region output current varies due to the change in input current. Output current is varying due to the change in input current. So that is our amplification. See, whatever input we are doing, whatever we are doing in the input, there should be a direct effect on the output. So that is only we want. So that is only we called as amplification or something else. Means the controlling on the output current. So that is done by input current only. So that can be possible in active region. So active region is used in amplification. So that was all about this common base. So in this common base, we understood all the concept related to this characteristic, input and output characteristics, and how it is varying. So now same thing we'll see for common emitter configuration. In common emitter, we'll be having this common emitter will be having the diagram like it will be like this. Means in this case, emitter terminal will be common. This is emitter, this is base, this is collector. So we have these three. Here we have JC, here we have JE, and this is VCE, and here we have IB, and we have BBE, BB plus minus. So this is our main. Ammeter is the common for input and for output. So in input we have base, and at the output we have collector, and the ammeter is common for both. So that is common ammeter characteristic. So for common ammeter characteristic, we'll be having input characteristic and output characteristic. So in input characteristic, we'll see how it is, what are the parameters which are there in input. That is, that is base current. So it is a plot of IB and VBE, IB and VBE, while maintaining VCE constant. Output voltage we are maintaining constant. Our current IB is varying with respect to VBE. So that is the plot between these two while maintaining VCE constant like this. So we can see here VBE, if we are varying, we are getting this. It is looking like diode characteristic, as I already told you. But VCE, it also affects. So at see, we can see here I have written IB is the recombination current. It flows when hole and electron recombination occurs inside base region. When it occurs in the base region, then only IB will be coming. Here note I have given that if BCE is increased, input characteristics shift towards right. So it is shifting towards right when we are increasing VCE. So that is happening. Now we'll see how it is. See, if VCE I increased, what will happen? VCB, it will get increased because base voltage it is constant. So VCB, the difference will be increasing. If it is increased, then effective base width, that is WB effective, it will get decreased. If it is decreasing, then recombinations, from here I can write here recombinations, number of recombinations, this will get reduced. Number of recombinations are reducing means what? IB reducing. So that is only happening here. If I'll increase VCB with this voltage, so what is happening at the constant value? Suppose any value I will take VBE, I'll see here that at the same value VCE, this is minimum VCE, then I'll increase, then I'll increase. So when I'll increase VCE, my IB is decreasing. When it is increasing like this, my IB will be decreasing like this. So same thing I have shown here. So if VCE is increased, input characteristic shift towards right. In this direction it is increasing. It is moving. So that is directly affecting the input current. VCE is directly affecting the input current. So I think we should take 5 to 10 minutes break. Maximum 10 minutes break we'll take, and then we'll start that output characteristic and all. Till here, any doubts if you have, immediately ask. Otherwise, we'll take break for 10 minutes. Okay. Now we'll come to the output characteristics. So in output characteristic, we'll see how it looks like. Here, okay. Yes, it is this. So it is a plot of IC versus VCE while maintaining IB constant. That is only here. So we have three regions here also. One is cutoff, other is saturation, third is active region. So in cutoff region, the graph where IB is equal to 0 and this and the right of this V is saturation. Sorry, this line it is there. So right of this and this graph, this is complete. It is cutoff region. We can see here. So this region is the cutoff region. Here, what is happening for NPN transistor? We have 0.2 volt for silicon and its value is 0.1 volt for germanium. So in cutoff, IB is equal to 0. If IB is equal to 0, IC we can directly write 1 plus beta ICO. And that is also called ICEO because IB is 0. So ICEO we can see here for silicon transistor I note ICO is in nanoampere. So hundreds of nanoampere we can say for silicon. And for germanium, it is in microampere. So beta will be, suppose beta will take 99. So IC will be in hundreds of microampere for germanium and hundreds of nanoampere for silicon. So for germanium, we have higher reverse saturation current. So we have IC, some IC value that is not exactly 0. That is not exactly 0 for germanium. For silicon, it is almost 0, we can say. For silicon, IC, it will be very less. We can say hundreds of nanoampere for silicon. And it is hundreds of microampere for germanium. So germanium value, it is not 0. It is microampere means it has some reasonable value. And for silicon, we can say it is negligible. So to make it completely 0, we need some voltage. So for silicon, we can say that VBE voltage for silicon, VBE for silicon or VBE saturation we can say, or cutoff we can say, not saturation, it is 0 volt. But for germanium, we need VBE some negative value, minus 0.1 volt something. Means that much negative voltage required to make IC 0 because we have some reverse saturation current in germanium. So we need to make it 0 for cutoff. So for that, we need some voltage, that is VBE voltage, to make it cut off. That is very negligible voltage we can use. Next is saturation region. Saturation region we can see here. The region of graph which lies above IB equal to 0, above this and to the left of BCE, means this region. This is not this much. This one is not. This is the reason. Here, up to here only. Above IB and left of VCE saturation. This region is the saturation region. In saturation region, IC depends upon both VCE and IB, because in this region we don't have IB 0, and in this region we don't have VCE 0. So it is depending on both values. So when transistor is in saturation, we can say VCE. In the next slide, I'll write for saturation. For saturation, VCE will be less than or equal to VCE saturation. Okay. So that is the main thing we need to remember, that VCE is less than VCE saturation and IB is greater than 0. That is above IB we will be talking. And next is active region. That is important region for any common emitter configuration. So in the active region, the graph, yes, anyone wants to ask? The graph which lie above IB and to the right of VCE means IB will be greater than 0 and VCE will be greater than VCE saturation. These values. So this is the active region. So in active region, we have IC constant. We have IC constant that is not changing, but we can say it is not changing in large extent, but it is slightly varying. Slight variation is there, but it is almost constant with respect to VCE. If we increase VCE, our IC is almost constant. So BJT is an active region. If BJT is an active region, in that case, I'll have IC is equal to beta IB plus 1 plus beta ICO. That is only. So now what will happen in this case? If we increase VCE, we are increasing VCE, our VCB, it also gets increased. If it is increasing, so in that case, effective base width, it decreases. If it is decreasing, in that case, our alpha will get increased and our beta also will get increased. So if both values are increasing, beta and alpha, means beta is increasing, then obviously our I will get slightly increased. It is not that much increased, but slightly increased. So due to increase in beta, IC increases with BCE. We say it is constant, but it is slightly increased. It is not increasing in that extent. So that is the main point here. So it is not increasing in that extent. So now we understood how IC varying in active region. If output characteristics are extended in backward direction, see some points I have written here. Just see. Early voltage. 1 minute. Here. If output characteristics are extended in backward direction, here I have shown some values. These are extended in backward direction. They intersect the voltage axis at common point, that is minus VA, comma 0. At this point, they are intersecting, where VA is called early voltage. Early voltage it is called, and it lies between 50 to 100 volt almost. Its value, it will be lying in this range. So what is happening at this saturation conversion point? Means before this it was in saturation, after this it will be in active region. So this is VCE saturation. If we take that we extend this in this direction, so we'll get some point where all these will intersect, and that point it is related to the early voltage. So we'll have this early voltage. Now what is the use of this early voltage? That we'll see. What is the use of this early voltage? Here we can see calculation of collector current when VCE is changing. When VCE is changing, we can calculate the collector current. That is the one point. We can change VCE, we can calculate current, collector current. Second thing, the calculation of output resistance of BJT. Any output resistance of BJT we can calculate by using this concept. How it will be, we will see later. Just you remember these points. The output resistance is reciprocal of slope of the output characteristic, because current and voltage graph it is. So it will be the reciprocal of this. So we can say if we take any point, at that point we'll see the reciprocal of slope of the output characteristic. So we can see we just here diagram we have here. If we take this slope here at this point, if we take slope, so what is the slope at this point? Or we say it is this point here. This is suppose IC1. 1 minute. Just I will show you. So here IC1 it is, here IC2, here IC3. So at IC1 if we'll talk, so we'll take the slope of this. What is the slope now? That slope will be IC1. Here I'll write slope is equal to IC1 minus 0 divided by VCE1 plus VA, because minus of minus VA, that is this. So I can write IC1 divided by VA, because VCE is almost 0, it is negligible value. So IC1 divided by VA in this case. Second case if we consider, so in second case slope I'll write something like IC2 minus IC1 divided by VCE2 minus VCE1. That is equal to IC2 minus IC1 divided by delta VCE. Right? I can write this. So these two slope will be equal as they are on saturation. So this slope and this slope, these can be equal. I can write IC2 minus IC1 divided by delta VCE is equal to IC1 divided by VA. So if I'll talk IC2 minus IC1 is equal to VCE delta VCE into IC1 divided by what VA. So here I can write IC2 is equal to 1 plus delta VCE divided by VA into IC1. So this is IC2 current I can calculate. Means whatever points I have written, I have given the next line, the calculation of collector current when VCE is changing, VCE1, VCE2. So there is a change from VCE1 to VCE2, that is delta VCE. If we change it VCE, we will get IC2. IC1, if we know, we can get IC2 here. So 1 plus delta VCE divided by VA into IC1. So that will get. See, all the points are not necessary, but only just you remember things what we can do by using this early voltage. So with this early voltage, we can also write the output resistance is reciprocal of the slope of the output characteristic. So that is R naught, I can write that is 1 by slope. That I can write here, and that is equal to VCE 2 plus VA divided by IC2. That we can write here. So these are the things. Now next point, these are the important things. Other things you have no need to remember, only this. So here we have, if early effect is negligible, the output characteristic will be perfectly horizontal. Means it will be a straight line. There will be no change in the IC current when we increase VCE. If there is no early effect, and the early voltage VA will be infinite, and such transistor has infinite output resistance, because it will become infinite VA, so that R naught will become infinite in that case. So output resistance will be infinite for common emitter. So that is for, there is no early effect in the device. So for that only it can be possible. So that point I mentioned here, just to remember. So we'll have a common collector configuration. We'll have question also based on the previous concept, but that question we'll take later, or in tomorrow's class only we can take. So here only just I want to finish this BJT and its related things. In tomorrow just I'll take few points which are left, and I will close it, this BJT characteristic. So only BJT, that basic things, and one more thing, how we can calculate the operation of BJT, in which mode it is operating. That also I'll show you in today's class. So now we'll come to the common collector configuration. In common collector configuration, we have one diagram, that is here we can see emitter, we can see base, we can see collector. Emitter will be like this. This is my collector, this is my base. This is collector. So here VBC, here VEC, or this is JE, this is JC, and this is, here current will be IB, and here current will be IE. So that is only, this is the diagram, actual diagram for common collector configuration. So in common collector configuration, we will have input and output characteristic both. So here we can see this input characteristic. It is a plot of IB versus VBC while maintaining VEC constant. That is only that same for others also. IB here, what is IB? IB is the recombination current, and VBC is voltage across the collector junction. That is voltage across the collector junction. If reverse voltage VBC is increased, IB gradually decreases and become 0. IB it is gradually decreasing. We can see the graph here. If we increase VBC, our IB will be decreasing and it will become 0. That just you remember, no need to go into the deep. That is not at all required for this in the exam, or they won't ask anything in this. So that is why I'll not take much into this. So now output characteristic. It is the plot of IE versus VEC while maintaining IB constant. So here few things. IC and IE are almost equal in magnitude, we know. Here we can say IC and IE. These are equal in magnitude, almost equal, because there is a slight change only. And VEC is equal to minus VCE. VEC is equal to minus VCE. That is. So Q plot of IE and VEC will be identical. See, whatever plot was there for IE and VEC, that will be same for this also. So whatever plot we made for IE versus VEC, same plot will be there for IC versus VCE. So there is no change, much change in this. So hence characteristic of common collector and common emitter configuration are identical. So we can see the output characteristic for common collector configuration, it is same as the output characteristic of common emitter configuration. So there is no much change in this. So I am not taking that in detail. So you can just see its output characteristic of common emitter. You will understand the same. The output characteristic of common collector is same as common emitter configuration. So that is done here. That is taken. So I think we understood with all the characteristics, input and output characteristics and their variation, input output, how it is varying, and the detailed configuration and application of all these devices will be coming in analog part. So that I have not taken analog part related things. But now I'll come to the another point, that is procedure to find a region of operation. How we can find which diode is working in which mode, or in which region it is operating, whether it is in cutoff, whether it is in saturation, or whether it is in active region. That how we get to know. So that is most of the times questions are coming in the exam, in the GATE exam and in other exams also they are asking questions. So we need to understand this clearly, so that the questions are mostly coming from this area, not from other area whatever I told. So here we can see, assume that the transistor is operated in a saturation region. First of all, that is our assumption. So in that, if we assumed that our transistor it is working in saturation, so we'll take values for VBE, that is equal to VBE 1 saturation. Saturated value we have taken. So this value it is 0.8 volt for silicon, and this value it is 0.3 volt for germanium. It is like this. Second thing, I'll talk about VCE. That is VCE saturation. And its value is 0.2 volt for silicon. And its value is 0.1 volt for germanium. So we have these, right? And it is for NPN transistor. Okay. For PNP, BJT's voltage are negative. Okay. So negative voltage we can take for PNP. Remember. And this is for these all for NPN BJTs. So that is the same main thing here, that we need to assume that our transistor is operated in saturation region. Second thing, calculate IB and IC independently. Their IB value and IC value we need to calculate independently. Means we will calculate IB, we will not calculate IC from this IB. So from input and output circuitry of BJT, we can calculate IB and IC. These are independent. Okay, so we cannot do here that IC is equal to beta IB. This we cannot take because if we take this, then we cannot understand whether our transistor is working in which mode. So that we cannot do, that we cannot identify. So IB we have to calculate separate and IC we have to calculate separate. This formula we cannot use. Third thing, calculate the minimum base current needed to operate transistor in saturation region. See, saturation values we have used here, PCE saturation. From this, I can calculate IB minimum that is equal to IC saturation divided by beta. That I'll use. IC saturation can be calculated from the BCE saturation values. In output, if we apply this KBL, we'll get IC saturation from output characteristic or output side. And from this IC saturation, we can calculate IB minimum. IB minimum now we calculated here. Now what we'll do in the next, we'll compare IB with IB minimum. So in this comparison, what is our assumption here? IB minimum we calculated separately and IB we calculated separately. If IB is greater than or equal to IB minimum, okay, if it is this, then transistor will be in what? Saturation. First. Second thing, if IB is less than IB minimum, in that case, transistor will be in active mode. And third, if IB is equal to negative value, IB, I got negative here from here, I got negative value, then transistor will be in cutoff. So these three comparisons we have to do, and with this comparison we can understand what in which region it is operating. So its region of operation we can understand from there. Okay, so I think it is clear to everyone. Any doubts if you have, please ask. Otherwise I have some other thing, that is next. For PNP BJT, both IB and IB minimum are negative for PNP BJT. So in that case, what we will do? Though both values are negative. So in that case, what we will do? We'll take magnitude of IV. That should be compared with the magnitude of IV minimum. So when we compare these magnitudes, what how we'll compare now? We have comparison concept. Here we have question, but before that, I'll do comparison here. What is the comparison? IB magnitude must be greater than or equal to IB minimum magnitude, and it says our transistor it is in saturation. Second thing, IB magnitude it is less than or equal to IB minimum. So in that case, our transistor will be in active mode. Okay. And third is IB that will be positive. So in that case, our transistor it is in cutoff mode. So that is, these are the comparisons we can do here. And with these comparisons, we can understand the mode of operation of any transistor in any circuit. So based on that only we decide. So sometimes they are asking questions with in which operation, in which mode it is working, or in which region it is working. Like one question I have taken here. The circuit shown, that circuit I have not made, I will make here. The transistor has beta 100, VVE saturation 0.8, VCE saturation 0.2. Find the region of operation. That they wanted to know. So I'll make a circuit here. What is the circuit? So here we can say so here 5 volt they have given. This is 50K. This is 3K. This is 10 volt. This is VCE plus minus, and this current is like this. So what we will see? We'll see current IC, we'll see current IV, and we'll see current I. This is VVE plus minus. So this circuit we can easily understand, and based on the parameters we'll identify in which mode of operation it is working, in which region it is working. So first of all, first point what I have given, the point is assume transistor is in saturation. So if we assume transistor is in saturation, so what we can do? We will do PBE is equal to VVE saturation, that is equal to 0.8 volt. Second thing, VCE is equal to VCE saturation, that is equal to 0.2 volt. These two things we can assume. Now from input, what we can calculate? IB is equal to 5 volt minus 0.8, that is BVE saturation, divided by its resistance, that is 50K. So from this I got how much? 0.084 milliampere in the first case. From the second output part I see, what we can do? This 10 minus this VCE divided by 3K. So 10 minus VC is 0.2 divided by 3K. What I'll get here? I'll get 3.26 milliamps. Now, third point, I'll do IB min. IB minimum, I'll calculate from IC saturation. That is IC saturation divided by beta. IC saturation is 3.26 milliamps divided by 100. So how much I'll get? 0.0326 milliamps. So these values I got 326. So here we can see IB, my value, this current, it is greater than IB minimum. If it is this, I can say my transistor, it is in saturation directly. There is no confusion in this. So likewise, we can do any type of question. We can solve any type of question. Only just we have to follow the concept. We have to follow the logic behind that. So whatever values they have given, whatever concept we know, we need to apply, and then we can find out in which mode it will be working, in which mode it is operating. So that is only. So now time it is almost over. So I'll close till here now, and I'll start. Few things are pending in this BJT, and few questions, if possible, I'll take, and I'll finish it on tomorrow. Tomorrow there will be a class from 9:30 to 11:30. So in that I'll finish it. I'll close it BJT, and if time permits, I'll start another topic also in tomorrow class. So now you can ask any doubts if you have in this, and otherwise I'll close it. Any doubts you have, please ask. Anything which I need to explain once again? Anything which is not clear? You can quickly ask. Yes, okay, sure. Either in the group or on tomorrow, I'll discuss one more problem. No problem. Okay. Definitely, I'll take one or two more problems so that it will be clear to you. Okay. Thank you so much. Bye. Good night. Take care. Yes, tell me. Any doubts related to previous classes? If you have, please quickly ask. You have time to ask. At last, I won't be able to answer because I don't know how much time I'll take for this topic. So if you have doubts, you quickly ask here in starting, so that there will be some flow in the concepts. So let me know if any doubts you have. Otherwise, I'll move on, and quickly I'll finish this. So I think everything is clear to you. Whatever I taught in the previous classes, it is perfectly clear. So now I'll come to the another topic. I have so many topics, but one of them, it is this one. So here we can see I have given heading, that is diode connected transistor. So do you have any idea related to this? what is this diode connected transistor? Sometimes in the exam they don't mention like this diode connected transistors. They sometimes they give only the diagram. What is the diagram? How it looks like? So that we'll see here. So diode connected transistors, as I have written in the theory, that if collector is shorted to base, it behaves as a diode. Such transistor is called diode connected transistor. Arrowhead indicates the direction of